everyone. I'm really pleased to be here today. Um, um, I think you're hearing a lot in the past couple of days about like AI in the summit. This is a very particular project where AI could really work for the good of humanity. It is really my pleasure to introduce you to our Giga project, where we're trying to leverage AI and machine learning algorithms to connect every child that attends school around the globe. So what is Giga? Giga is a school connectivity project. It's a joint project between UNICEF and ITU. And the problem that we're tackling today is that we have nearly half of the 6 million schools in the world are not connected. More than 500 million students around the world have no access to any online content. And then, of course, this feeds into the global ITU statistics, where today we have 2.6 billion people that are unconnected. So 1/3 of the global population around the world that is not connected. Giga's mission is to connect every school in the world to the internet by 2030, in alignment with the SDG goals also by 2030. And in order to tackle such a problem, we identified a four-pronged strategy. Mapping all the schools and monitor the school connectivity status in real time. Model, the second pillar, model the infrastructure, the policies and the regulations that will attract the right investment needed to deliver school connectivity. Financing and helping supporting governments to build the right layered financing to pay for this connectivity and to make it sustainable. And lastly, contracting to support governments in their procurement processes to contract and procure the equipment for such connectivity projects. I will stop there now and hand it over to my colleague Ivan from UNICEF.
Thank you. Thank you, Walid. It's a pleasure to be here. I'm going to go over first what we're going to talk about today, which is two topics and other research that we do, basically mapping of the schools, mapping and planning for the connectivity infrastructure and other applications. So I'm going to start with the machine learning for school mapping. As you probably know now, after 2 slides and what Walid has said, our goal is to connect all the schools in the world by 2030. And for that, first, we need to know where they are. So we do that trusting the governments and their collection systems and their enumerators, but we also use machine learning assisted algorithms to do that. I'll explain in a second how we do this, but basically we rely on data and on our partners to give us high resolution satellite imagery, like Maxar, and we also rely on high performance computing that's generally given to us by our partner Dell. Now, we've developed several machine learning models for predicting schools versus no schools in different countries and in different regions around the world. And our models are good enough in the sense that they tend to have performances over 90%. Now, the way we do that currently is in these 7 steps that you can see here. As you can see, like 3 out of them are about data. So the first part is always about data and having the right data. One thing we do is we consolidate different data sets, not only looking at what the government gives us, but also looking at public sources like OSM and Overture maps. We also, at the same time now, have to download in a second step all the images from the satellite tiles for those locations that we have, and then we have an extra step of cleaning and curating that data so we have the right data set to train our models. The next step is model development. We tinker with several deep learning architectures to develop the model that's going to be able to predict schools versus no schools. Then we have a phase of model improvement, and then what we call model deployment, which is when we look to see if other regions in the country of interest have schools in them. And finally, the last step is model validation. Let me again just stop for a bit on the first one, data curation and pre-processing. So again, as I said, we gather school locations from other sources, and then we combine them and we look for duplicates, and we get them out of what is the training set. So now that this doesn't mean that these are not valid schools, they're just not schools that are valid for our training set to train the model. Now, the model development and part of the model deployment goes like this. As you could imagine, you have a set of schools and a set of non-schools image tiles that become the training and the test set for our AI models. With that, we get the accuracy, this over 90% F1 score in this case. And then this would be the part of what we call model deployment, when we download the tiles of all the country and we look for schools using that trained model in the label data set. Now, the model improvement part contains things like this. The tiles that we use are 300 by 300 meters, so sometimes the schools are not occupying the whole extent of the tile. So we try to pinpoint the exact location by using somewhat state-of-the-art techniques like activation maps to pinpoint the right location of the schools. Finally, in the validation, we're now also providing a validation app that we call for the countries and country offices to be able to say whether that is really a school or whether no, that was not a school. That fits back into our data set and allows us to retrain the model once we have more validated and validated data. And with that, I'll pass it again to Walid for the next part. Thanks.
Thank you, Ivan. So once our UNICEF colleagues took care of the schools and the mapping, now we're going to tackle the second pillar, modeling. And in this pillar, we look at the infrastructure and modeling and designing and planning for how we can fill in for the gaps to build these connectivity projects and deliver them to the schools. So let me take a step back and explain to you the problem, so just to give you a glimpse of what we're trying to solve. First of all, we need to understand the existing infrastructure and assess the infrastructure proximity. So we need to be able to answer questions like, what is the percentage of a population near X kilometer from a certain feature of infrastructure? How far is a school or a certain point of interest is from the nearest fiber node? And that will be able, like in that process, it comes into like two sub-problems. So the first sub-problem is to identify and collect the data, such as what you could see here on the top left here, fiber routes and road layers, etc. How can we collect that data? And the second sub-problem is that once we understood the data and the existing lay of the ground, like how can we augment that and build and design and plan for the connectivity project and build in the right networks to deliver connectivity? And that will lead us to like things of like insights to see like color-coded regions by priority and assess like how big is the gap. So certain regions will have a bigger gap and certain regions will have a lower gap. Then we have to focus the investments on the region that needs it the most to deliver the connectivity. So how are we leveraging AI and machine learning to solve these problems? On the sub-problem about designing and delivering projects, we are leveraging machine learning techniques for optimization. So here I'm showing you an example of a school connectivity kind of problem description. The red dots on the screen show non-connected schools. The green dots show fiber nodes. We leverage a heuristic algorithm, we leverage heuristics to minimize distance between every pair of schools of what needs to be built. In this case, we need to plan for fiber routes, the yellow lines here, and we need to plan them in a way that minimizes the overall distance of the overall project. And so we use minimum spanning tree algorithm to design yellow lines to connect the yellow dots and to connect the red dots to the green dots and turn them into connected nodes and expand the algorithm to a whole region. So we're leveraging that, and you could see the algorithms in play here in this map where we're running the algorithm between different locations and building the fiber routes that are required at the national level. So it's also a big data problem. The second sub-problem that we're trying to solve is to identify, to automate the data collection part. It's really hard to understand where does the existing infrastructure is today. And that's a quite hard problem because we don't have enough resources to document all this and collect the data manually. So we need to do some automation. And to that aspect, we're working with a satellite imagery provider to look into high resolution imagery, satellite imagery, and we run and we train AI models in order to be able to extract infrastructure features, including electricity, grid information, and information about the densification of the existing network. And we do like some fine tuning by putting a human in the loop in order to like review the information that is provided by the AI, by the trained AI model, and that's a way to enhance the precision of our AI model. And our goal is to make all this available through open source by publishing digital public goods for identifying infrastructure features and making these infrastructure sets available for the whole community, so the whole community could participate in tackling the problem and finding the solution to connect every school in the world. Now, I'll hand it over back to Ivan so he can walk you through the other aspects of the...
Thank you. Yeah, so I'm just going to go briefly over the last part of the presentation. Hopefully it was short enough, and it's other applied research projects that we do. Walid has already explained to you just right now the issue of the fiber connectivity, and we're working very closely with our colleagues at ITU to expand this also to deal with multiple technologies like satellite, cellular, and radio. And I wanted to take the opportunity to just make a claim in this venue where most of what we're listening to is machine learning, and I wanted to just point out that this is a combinatorial optimization problem, and actually search and optimization are the foundations of artificial intelligence. If you think about it in a broad and naive aspect, what you're doing when you're training a deep net is basically doing a search, optimizing the value of the parameters of your deep net so that it optimizes in classification the distance between the labeled examples that you have of the different classes. So just when you don't have weights in a deep net that are continuous, but you have variables that have discrete values, then we come to what's called combinatorial optimization. And there's a whole theory of complexity, and you might have heard of this P versus NP problem, which if you solve it, it's $1 million. I still think today you can get that money. And what I wanted to point out right now is that even for just connecting fiber, and we're not going still beyond other technologies, but just for that, if you were to connect these points in a straight line, that's, as Walid has said, an easy polynomially solvable problem. It's minimum spanning tree from graph theory, if you guys know. As soon as you add roads, and roads can have forks, and you have to, let's say, split the fiber, that becomes an NP-hard problem. It reduces to the Steiner tree problem. So that's basically something that's exponentially hard to solve in the worst case. Now, when we do all the technologies, or we add a budget in which we say you have to connect the more schools you can with that budget, already for the line of sight issue, it's already an NP-hard problem, and it's a Steiner problem. So these are very hard problems, and maybe the optimization is not something that we've talked about a lot in this venue. And just to end very quickly, we're also working on creating what we call the Giga ML utils. That's a Python library for assisting in doing classical machine learning with feature processing, model parameter hypertuning, model selection, and model evaluation. We're also tinkering with new feature embeddings specific for satellite images. And we're also starting to work on time series analysis as it relates to quality of service data that we get from the schools that we connect. And as Walid said before, all of this is open source, and hopefully we'll have your help to move this further and expand it. And since we have 20 seconds, I don't know if Walid, you want to say something final?
No, just echoing what you were saying, Ivan, it's an NP-hard problem to solve, connecting every school in the world. So please join us in trying to tackle that problem.